Hello, welcome to Algebra 1 with Miss Betsy. This is part 2 of a lecture on motion problems in two variables. So if you are tracking along with me, I'm using as my text Algebra 1 for Christian Schools. It's published by Bob Jones University Press, and I am on page 300, section 7.7. What we showed in the last video was an example of how to use a motion problem where you have vehicles traveling towards one another. Same general principle if you have vehicles traveling at different rates of speed but going the same distance, if you're traveling opposite directions from one another, where you are, the only variable that you're having to consider is the amount of time that they travel and the speed at which your objects are traveling. Another type of motion problem that you have involves resistance. And an example of this would be riding a bicycle into a headwind, making a round trip, but you're out riding your bike on a windy day, which is what I do, and you hate it when you're going into that wind, but you love it when you're going with the wind at your back, because you work harder, you make less progress when you're pedaling your bicycle into the wind, but you turn around and that wind just pushes you along. So you have the effect of wind, the effect of airspeed when you're running, when you're bicycling, when you're rollerblading, when you're flying an airplane, when you're, I'm sure, hot air ballooning, all sorts of things. The speed of the air, and if it's at your back or in your face, impacts how much progress you're able to make. Another type of motion problem where we're working against resistance is water problems, where you have the rate of the current to deal with. If you're paddling upstream, paddling a canoe upstream against the current, not near as much fun, not near as fast as turning around and going downstream, for the same reason as what we were talking about with airspeed. When you paddle upstream, the current is working against you. When you paddle downstream, the current pushes you. So for example, let's say that you are paddling 3 miles an hour, and 1 mile an hour here is going to be my steps. I'm going 3 miles an hour. 1, 2, 3. But the current is pushing against me 1 mile an hour. Well, that pushes me back. So it's the 3 steps forward, 1 step back. So instead of traveling at a rate of 3 miles an hour, your actual effective progress is 2 miles an hour. That's what we're going to talk about in this problem. This is on page 301. And the example says this: when his Sunday school class went canoeing, Bill paddled 12 miles down the river in 3 hours. After paddling back upstream for 2 hours, he had traveled 4 miles. We have 2 questions. How fast does Bill paddle in still water? The second question is, what is the rate of the current? Now that right there screams out at you the definition of 2 of your variables. Remember, we're using 2 variables to solve these equations in this chapter because we're using simultaneous equations. So what is it that we're trying to find, first of all? Well, we're trying to find Bill's rate, and we're trying to find the rate of the current. So let's just start off right at the beginning. I'm running out of red on this. Let x equal Bill's paddling rate. And if x is the speed at which Bill paddles, then let's have y be the speed of the current. Now remember, think about this. If you're paddling at a set rate, the speed of the current is going to affect you. When you're going downstream, which is what I would have done if I was on this trip, you do the hard part first. You go upstream and then come back up downstream, so that the second part of your trip is the easier one. Anyway, back to the problem. Bill's paddling rate is going to be reduced by the speed of the current when he's going against it. It's going to be increased by the speed of the current when he travels downstream. And that relationship between those two pieces of information is something that, even if right now you just need to memorize it, that's a key important piece of information for dealing with these problems. So if we look at our book, we need to see what information can we collect. So let's say, first he went downstream. So what info do we have? Well, you look at your book and it says, 12 miles that he traveled. And how long did he paddle? He paddled for 3 hours. Okay? See what happened when he traveled back upstream. How long did he work? It says he paddled upstream for 2 hours. And how much progress did he make? Well, before I answer this, how many miles an hour was he traveling over here? Well, 12 miles, 3 hours. He was averaging 4 miles an hour. Pretty nice speed. Nice gentle speed going downstream. But in 2 hours, when he was paddling upstream, he only made 4 miles. So his effective speed going upstream is just 2 miles an hour. But that's not what we're looking for right now, is it? What does our problem want us to determine? It wants us to know his paddling rate and the speed of the current. We see his effective rate downstream is 4 miles an hour. His effective rate upstream is 2 miles an hour, but it's a combination of two different speeds, and we have to figure out what those two different speeds are. So, why don't we come up with rate times time is equal to distance for our traveling time upstream and our traveling time downstream. So we're going to say upstream, downstream, and we have rate times time is equal to distance. Rate times time is equal to distance. Now you can't just put an x and y in here for the rate, can you? Because our rate of travel going upstream is a combination of these two rates. Our rate downstream is a combination of these two rates. And remember, I did the travel forward 3 miles, 3 steps, but the current pushes you back 1 step. And then the current pushes you forward when the current's at your back. So what's our rate going to be upstream? Well, it's going to be Bill's paddling rate, which is x. Always going to be affected by how fast you're traveling. But then the speed of the current is either going to work for you or against you. If you're going upstream, that current's working against you. It's pushing you back. So you subtract the rate of the current when you go upstream. Your rate of travel downstream is, of course, how fast are you paddling? And then how does the speed of the current impact you? It's pushing you along, so you add the rate of the current. This type of relationship right here between the two different speeds is key to being able to figure out motion problems in two variables that involve a current or a wind speed. If you can't get this piece of information here, the relationship between the two speeds, then you won't be able to solve the problem. Once you do understand that relationship, then it's pretty straightforward basic algebra. What's the time that he traveled upstream? Upstream he traveled 2 hours. Downstream he traveled 3 hours. And we know that rate times time is equal to distance. Rate times time is equal to distance. So we're going to have 2 times x minus y, 3 times x plus y for the distances that were traveled here. Now, what do we have to do next? We have to come up with 2 equations that we can solve at the same time. So looking here, does anything jump out at you? With our last problem, we combined distances. So we combined the travel to say that this piece of travel plus this piece of travel, this distance, when you combine them, they equal the total distance between the 2 towns. But we don't have anything like that going on here, do we? No, but we do have, if you look at this chart, you can see that we used 3 hours, we used 2 hours, we used X, we used Y, but we still haven't done anything with 12 miles and 4 miles. What is 12 miles? Well, 12 miles is the distance that he traveled. 12 miles is not the distance here. 12 miles is the distance that he traveled downstream. 4 miles is the distance that he traveled upstream. So we're going to use those pieces of information to come up with our 2 equations. So we have 2 times the quantity x minus y is equal to the distance that he traveled upstream, 4 miles. 3 times the quantity x plus y is equal to the distance that he traveled downstream, which is 12 miles. Now, what are we going to do to solve these 2 equations? Remember, we want to be able to eliminate one variable. Now, you might think at first, let's go ahead and distribute this, and we'll have 2x minus 2y is 4, 3x plus 3y is 12, and then we'll multiply by 3's and 2's and cancel variables. Well, that would work to go ahead and do the distribution, but why don't we do it a little bit in a little bit easier manner? Do you see something that I see? Well, yeah, why don't we just go ahead and divide both sides of this first equation by 2. What happens if you do that? We put this teeny little red in here. We divide the left hand side of the equation by 2. We end up with x minus y. Divide the right hand side of the equation by 2. We now have x minus y is equal to 2. What's going to happen over here? 3 times the quantity x plus y, we're going to want to divide that by 3. And we have x plus y is equal to 4. Now we have 2 equations that are very easy to solve simply by adding them. We have, when we add these 2 equations together, our y's drop out. 2x is equal to 6. Divide both sides, we have x is equal to 3 miles an hour. 3 miles an hour what? That's Bill's paddling rate. What is y equal to? Y is equal to 1 mile an hour, which is the rate of the current. So Bill's rate upstream is 3 minus 1 which is 2 miles an hour. Remember we said earlier that the effective rate going upstream was 2 miles an hour. The effective rate going downstream here is 4 miles an hour. And that's exactly what we ended up with, isn't it? Bill's rate of 3 miles an hour plus the rate of the current, 1 mile an hour, gives us his combined speed, or his effective rate of travel, of 4 miles an hour when you go downstream, and the speed of the current affects you positively. When you go upstream, the speed of the current affects you negatively. We saw that that speed was 2 miles an hour, and it works. If your paddling rate is 3 miles an hour, you subtract the 1 mile an hour that the current pushes against you, and you do get 2 miles an hour. Now, take some time. These are not problems that most of you are going to be able to sit down and complete in 2 minutes. They take some thought, they take some reasoning to go through them, but it's well worth your investment time, because you will see motion problems for the rest of your time in math. So dig in there, ask the Lord to help you make the connections that you need to make to see relationships between pieces of information in the problem, and enjoy yourself. I'll see you next time.